Today, we'll discuss some of the conceptual questions and numericals on capacitors. So let's take the first question. Two protons A and B are placed in between two plates of a parallel plate capacitor charged to a potential V as shown in the figure. Which of the two protons in the figure experiences greater force? You can see that between the two plates of a capacitor, we have two protons A and B. And it has been asked which one experiences greater force. Now you know that electric field between the plates of capacitor, this is given as E equals to sigma by epsilon naught. And sigma, as you know, that this is your Q by A, as it is the surface charge density. So this expression of electric field is independent of distance. And as it is independent of distance, and if you want to find out the force experienced by the protons, this will be given as your Q into E. So obviously, this will be Q, capital Q, A epsilon naught. This is independent of distance, so both the protons A and B will experience same force. Next question. The graph shows the variation of potential V across the plates of two capacitors A and B versus increase in charge Q stored in them. Which of the capacitors has high capacitance, and give reason for your answer. Now you know that relation between charge, capacitance and potential difference, this is given as Q equals to Cv. So obviously this will be C, which is coming as the slope for the graph if it is plotted for Q and V. But here it is the graph of V and Q. So obviously it is the reciprocal of the capacitance. Okay. So if it is the reciprocal of capacitance and it is asked which one has higher value of capacitance, obviously in this case A will have higher value of capacitance because for this one, this slope is less and here it is in the reciprocal of the slope here. Because if you take V, this is 1 by C into Q. So for this one, A will have higher value of capacitance. Next question. The given graph in figure shows the variation of charge Q versus potential difference for two capacitors C1 and C2. The two capacitors have same plate area, but the plate area of C2 is double that of C1. Which of the lines in the graph corresponds to C1 and C2 and why? Now you see, as C equals to epsilon naught A by D. Now in this one, it is given that the two capacitors have same plate separation. That means D is same, but the plate area of C2 is double that of C1. So obviously, for capacitance, if you take C2 will have value epsilon naught 2A by D, and for C1 we can write this as epsilon naught A by D. And if you take Q equals to Cv, so obviously A will have a slope more than that of B. A will represent C2 and B will represent C1. Because the slope of C2, here a value of C2 is more, and for A the slope is more. So obviously A will represent C2 and B will represent C1. The figure shows a sheet of aluminium foil of negligible thickness placed between the plates of a capacitor. How will its capacitance be affected if 1. The foil is electrically insulated, and 2. The foil is connected to the upper plate with a conducting wire? Okay, for this question, you can see these are the two plates of a capacitor, and between the plates of capacitor we have a thin foil of aluminium. which is placed between the two plates of this capacitor. Now, so this can be treated as a case of capacitor with a conducting slab between the plates. And you know that the expression for capacitance of a parallel plate capacitor with a conducting slab, this is given as epsilon naught A by D minus T. Now for this case, as the foil has negligible thickness, so T will be 0, and if it is 0, that is C equals to epsilon naught A by D. This simply indicates that the capacitance will remain, or it will remain the same, because the thickness is very small, so we can take that the capacitance will not change. Alternatively, you can treat this also as a case of two capacitors which are joined in series. And if we consider that this is a plate of negligible thickness, so that means here for these two cases of the capacitors which we are getting, say for this one as C1, this one as C2. So this will be a case of C1 being epsilon naught A divided by D by 2, and C2 is also epsilon naught A by D by 2. And these two capacitors, we can consider that they are connected in series. So if they are connected in series, the formula will be your C1 C2 divided by C1 plus C2. As the values are same, so you'll find that ultimate value will be epsilon naught A by D. Next question. A parallel plate capacitor is charged by a battery which is then disconnected. A dielectric slab is then inserted in the space between the plates. Explain what changes, if any, occurs in the value of first capacitance, second potential difference between the plates, third electric field between the plates, and the fourth the energy stored in the capacitor. For this question, we have the parallel plate capacitor which is charged by a battery, and it is then disconnected. So once it is being charged, then the charge Q will appear on the plates, and after that we are disconnecting it. Now using a dielectric medium or dielectric slab between the plates of capacitor. So if that dielectric medium is filling the gap, and you know that if it is there, the capacitance will be now K times epsilon naught A by D. So the capacitance will increase. So for the first part, it increases. Now second is, what happens to the potential difference between the plates of the capacitor? Now you know that if a dielectric slab is used between the plates of capacitor, or dielectric medium is there, so if the dielectric medium is introduced, then electric field decreases. So electric field here will become E naught by K. As a result, the potential will also become equals to V naught by K. That means it will become 1 by K times the original value. That means we can say that it decreases there. Third is, what will happen to the electric field? Obviously, electric field, as we have discussed here, this will also decrease. So this electric field is also decreasing in this case. And the last one is the energy stored in the capacitor. So if you take the energy stored in the capacitor, so for this energy stored, now for this case, what we should use, which formula we should use? We have the formula like Q square by 2C, half CD square, or half Q into V. Now you can see, if the capacitor was charged and then it is disconnected, that means the charge stored on the capacitor has remained the same. So in this case, we will be using the formula Q square by 2C, where as Q is same. So obviously, if the capacitance of the system is increasing, so energy stored will decrease. Next question. A parallel plate capacitor is charged by a battery and the battery remains connected. A dielectric slab is inserted in the space between the plates. Explain what changes, if any, occurs in the value of the potential difference between the plates, capacitance, electric field between the plates, and energy stored in the capacitor. Now this question is similar to the previous one. Only difference is that in this case, the battery remains connected. For this case, as we have kept the battery remain connected with the plates of capacitor when the dielectric medium is introduced between the plates or dielectric slab is used between the plates, so obviously the potential difference will remain same because it is connected to the same source. So V remains same. Now for the second one, it is asked what happens to the capacitance. Now capacitance, as we have used dielectric medium between the plates, so capacitance will become equals to epsilon naught A by D into K. That means it will become K times. For the third case, electric field between the plates. Now here in this case again, as the V has remained the same, so obviously electric field between the plates will also remain the same. So this E will also remain same. And the fourth one, that is the energy stored. Now we know that it is your half CV square because in this case V has remained the same. So as C is becoming K times, so this will become K times because this is becoming K times. Now let's take the next question. In a parallel plate capacitor with air between the plates, each plate has an area of 6 into 10 to the power minus 3 meter square and the distance between the plates is 3 millimeter. Calculate the capacitance of the capacitor. And next part is, if the capacitor is connected to 100 volt supply, what is the charge on each plate of the capacitor? In this case, everything is given, plate area, plate separation. So for parallel plate capacitor with air between the plates, formula is your epsilon naught A by D. So epsilon value we have put here, 8.85 into 10 to the power minus 12. Plate area value is 6 into 10 to the power minus 3, so that we have substituted. Just take care for D. D is given in millimeter, which is the plate separation. So don't forget to convert that to meter. So it is 3 into 10 to the power minus 3. So ultimately it will become 17.7 into 10 to the power minus 12 farad. For finding the charge on the plates of capacitor, we have the formula Q equals to CV. So it is 17.7 into 10 to the power minus 12 and the potential difference is 100 volt. So finally it will be 17.7 into 10 to the power minus 10. Let's take question number 8. Explain what would happen if in the capacitor given in the previous problem, a 3 millimeter thick mica sheet of dielectric constant 6 were inserted between the plates, while the voltage supply remained connected. And second part, after the supply was disconnected. So let's take this question. In first part, the voltage source remained connected. So as the voltage source is connected to the capacitor, so obviously capacitance, and after that we have inserted the dielectric slab between the plates of capacitor. So new capacitance will be K times epsilon naught A by D, because you can see that the thickness of the dielectric slab is same as the plate separation between the plates of capacitor. So it is your K times epsilon naught A by D. If you just substitute the values, K is 6, is 8.85 10 to the power minus 12 into area 6 into 10 to the power minus 3 divided by separation 3 into 10 to the power minus 3. So it will come out to be 106.2 into 10 to the power minus 12 farad. If you calculate the charge, it will be your C into V. So C is 106.2 into 10 to the power minus 12. V is 100. So it will be 106.2 into 10 to the power minus 10 coulomb. So this is for the first part. In the second part, it is said that the source is disconnected. And after that, we are inserting the dielectric slab. So when the source is disconnected, obviously it means whatever charge it has acquired till that time, it will remain on the plates of capacitor. So if you want to calculate this charge, it will remain Q equals to C into V, where C will be the capacitance of air-filled capacitor, because we are using dielectric slab or inserting the dielectric slab after it is disconnected. So it is your epsilon naught A divided by D into V, which is 100 volt. So if you calculate, it will be same as 17.7 into 10 to the power minus 10 coulomb, what we have got in the previous case. Now let's take a potential difference. So it is V dash, which will be equals to now Q by C dash. Now Q is this one, which we have calculated, and new capacitance after the introduction of the dielectric slab, it is K times the capacitance of air-filled capacitor. So it is K times C. So it is 1 by K, Q by C. Q by C is your V, so it is V by K, or it is 100 by 6. That is your 16.67 volt. Next question. Two parallel plate capacitors X and Y have the same area of plates and same separation between them. X has air between the plates, while Y contains a dielectric medium of dielectric constant 4. Calculate capacitance of each capacitor if equivalent capacitance of the combination is 4 microfarad. Second part, calculate the potential difference between the plates of X and Y. Third part, estimate the ratio of electrostatic energy stored in X and Y. Now for this case, let's take, we have X and Y as the two capacitors here. Between the gaps of the second capacitor Y, we have the introduced a dielectric medium of dielectric constant 4, and it is connected to a 15 volt supply here. Let's represent capacitance of first capacitor as C, Cx, we are writing it as C. And as it was given that they have the same plate area, same plate separation, and in between the plates of capacitor Y, we have introduced a dielectric medium. So in this case, the capacitance of that will just become 4 times the capacitance of the first capacitor. So it is your 4C. And as they are connected in series, so in this case, equivalent capacitance, this will be your C into 4C divided by C plus 4C. We are using the formula for parallel combination, series combination, as if two capacitors C1, C2 are connected in series, then the equivalent will be given by the formula C1, C2 divided by C1 plus C2. So this will become equal, and this equivalent capacitance, so if you substitute, it will C into 4C divided by C plus 4C. So, and equivalent capacitance value, that is already given as your 4. So this is your 4C square by 5C, and that is C equals to 5. So C is equals to 5 picofarad, and so Cx is your 5 picofarad, and Cy, as it is 4 times, so it will become 20 picofarad. This is the answer to first part. Now second part is potential difference between the plates of X and Y. Now as the two are connected in series to a potential difference of 15 volt, and Q is equals to CV. if you consider, since it will be the same charge flowing through both the capacitors, so obviously for same charge, V will be inversely proportional to C for same charge. Obviously, it will be in potential difference will be in inverse ratio of their capacitances. So capacitance ratio is 1:4. So potential difference ratio will be 4:1. So that means if you take potential difference across X, this will be 4 by 5 into 15, that is 12 volt, and across Y it will be 1 by 5, that is 3 volt. So it is 12 volt across X and 3 volt across Y. Similarly, if you have to find the energy stored in X and Y, as it is the same charge, so energy, this is your half Q square by C. So again, energy ratio, if you take, it will be in inverse ratio of the capacitance. So as it will be in the inverse ratio of the capacitance, so this will be equals to, again, 4:1. Let's take question number 10. A capacitor of unknown capacitance is connected across a battery of V volt. The charge stored in it is 360 microcoulomb. When potential across the capacitor is reduced by 120 volt, the charge stored in it becomes 120 microcoulomb. Calculate the potential V and the unknown capacitance C. And second part, what will be the charge stored in the capacitor if the voltage applied has increased by 120 volt. For this question, let's start with the basic formula, Q equals to Cv. Now it is given that the charge is 360 microcoulomb and is C into V which we are taking. Let's call this as equation number 1, because here capacitance value as well as the potential difference both are unknown. In the second case, when we are changing the voltage, the charge has become 120 microcoulomb and it will be the same value of the capacitance. Potential difference is now, since it is decreased by 120 volts, so the new potential difference will be V minus 120. This is the equation number 2. Now if you take equation 1 and 2, so in that case we will get V by V minus 120 as 3, or V equals to 3V minus 360, 2V is 360, that will give V equals to 180 volt. Now for finding the charge, as we are using Q equals to Cv, so it will be equals to, or charge is already given 360, so for the value of C, it will be 360 equals to C into 180, and that gives the value of capacitance as 2 microfarad. In the next part, it is asked, what will be the charge stored if the voltage is increased by 120 volt? Remember, the voltage we have derived expression as 180 volt. So new voltage now will be 180 plus 120. So capacitance value is already we have obtained. It is 2 microfarad. So it is 2 into 300, that is 600 microcoulomb, and that is the answer. In question number 11, obtain the equivalent capacitance of the network shown below. For a 300 volt supply, determine the charge and the voltage across each capacitor. This is the network shown here. You have to find equivalent capacitance of this network. Now, this is your, we are representing by C1, this C2, C3, and this is C4. Now, from the diagram, it is clear that it is first one, C1, it is in parallel with C2 and C3 series combination. But here students make a mistake. They take this C4 also to be in parallel with the circuit, which is not correct. In fact, if suppose I pull this point here, in that case, this will appear as if you have a C4 connected and it is like this. So, in fact, you'll find this C2 and C3, they are in series. This will give the value of 200 picofarad in series, giving you a value of 100 picofarad. This is in parallel with C1, which is also 100 picofarad. So these two, now they are in parallel, giving you equivalent capacitance of 200 picofarad, and this is in series with this 100 picofarad C4 capacitance. So these two, they are again in series, giving you the value of equivalent capacitance as 200 into 100 by 300, and that is 200 by 3 picofarad. This is the value of equivalent capacitance. Now, let's try to find out the charge and the voltage across each capacitor. Now here, if you consider the given circuit, we have equivalent capacitance shown here to be 200 by 3 picofarad. Voltage is your 300 volt. So we can find the charge flowing through the circuit, Q equals to CV, which is 200 by 3 into 300, and which is equal to 2 into 10 to the power 4, and since it is your pico, so it is your 10 to the power minus 12, and that is 2 into 10 to the power minus 8 coulomb. This is the charge flowing through the entire network of the capacitor. So, if you consider the charge flowing through C4, which we represent suppose by Q4, so this will be your 2 into 10 to the power minus 8 coulomb. If you consider a potential difference, then potential difference also we can get V4 as charge which is flowing through this, which is your 2 into 10 to the power minus 8 divided by its capacitance. So its capacitance was your 100 picofarad. So this will give you value of 2 into 10 to the power minus 8 by 10 to the power minus 10, which is 200 volt. Now, 2 into 10 to the power minus 8 coulomb is reaching here, and it has two branches to flow. Both have equivalent, have the same value of capacitance, this 100 and 200 in series, that is also giving you equivalent capacitance as 100 picofarad. So obviously the charge will get equally divided. So the charge through C1 will become 10 to the power minus 8 coulomb, and through C2, and this is Q1, and Q2 will be same as Q3 because these two are in series. So this is also equal to minus 10 to the power minus 8 coulomb. Now, if you consider the potential difference, now since we have already got the potential difference across C4 as 200, The total is 300 here. So obviously across this it will be 100 volt left. So the voltage across C1 will be equal to 100 volt. Now that 100 volt is now in this part. It is equal across these two. So it will be V2 and V3 both equal to 50 volt. So this is the charge across the circuit, charge across each capacitor, and also the potential difference across each capacitor. Question number 12. Find the equivalent capacitance between P and Q for network of capacitors shown below. This is the first one where we have 5 capacitors connected in this pattern. This particular network is called your Wheatstone bridge arrangement, where none of these capacitors are directly in series or they are in parallel, except for the case if the values becomes equal or they have a specific ratio there. And we get a balanced condition of this one when C1 by C2 ratio is same by as C3 by C4 ratio. If this ratio of the capacitors is equal, then it is said to be in balanced state, and in balanced state no charge flows through this capacitor, that is C5. So here also you can see, although the appearance wise it will appear to be different, but if you just consider that if I pull this point here, suppose I am pulling this one to this point and this point here, then the same can be drawn like this is your P. This one will come to this place. This 2C will come here. And if I suppose call them as point 1 and 2, let this be point 1 and this be 2. This one will come here, C, and this 2C. Whereas between 1 and 2, you have this capacitor, C. So this is your C, this is your 2C. This is point Q. So basically, this is same as Wheatstone bridge arrangement. It is in the modified form. Here. Now you can see that this is C1, this is C2, this is C3, this is C4, and the ratio C by 2C, C by 2C is equal. So in this case, it is in balanced state of Wheatstone bridge. So if it is in balanced state of Wheatstone bridge, no charge will flow through this middle one, that is C5. So that means it will not flow through this. So if you consider now that no charge is flowing through the middle one, we can assume as if this charge capacitor is not present here. And if it is not there, then you have C and C in series, giving you equivalent capacitance as C by 2. This 2C and 2C, they are also in series, giving you equivalent capacitance as C. And then these two between points P and Q are basically connected in parallel. And if these two are connected in parallel, then the equivalent capacitance will be given as 3C by 2, which is simply C1 plus C2. So this is your first part. In the second part, it is given, we have capacitors shown C1, C2 and C3. If it is only C1, C2, C3 shown like this, it is very easy to say that they are in series. And we can find their equivalent capacitance using the formula 1 by C equals to 1 by C1 plus 1 by C2 plus 1 by C3. But it is given there in the problem that this is connected like this with the help of a conducting wire, you can say. So it is like this. And if it happens like this, suppose I take this point as 1 and this 2. So obviously you can say, as it is a conducting wire, potential difference between P and 1, it will be 0. Because it is connected by a conducting wire, so it is equipotential there. So if we redraw this one by taking the points of same potential being represented at the same point. So if I have point P here and 1, I can represent it at 1 point. Similarly, Q and 2, they will be also at the same potential. So it is point Q and 2 at the same point. Now, if you take C1, it is basically connected between point P and 2. P is here, 2 is here. So we can represent this capacitor. We have represented this. Between Q and 1, you have C3. This is your C1. So it is between 1 and Q. 1 is here, Q is here. So we can show C3 here. And between point 1 and 2, you have C2. So 1 is here, 2 is here. So it is like this. Now it is very much clear from the diagram that C1, C2, C3 of this network is basically in parallel. And if they are in parallel, so equivalent capacitance will be C1 plus C2 plus C3. For this type of network, you can easily represent them by taking the points which are at the same potential to be at same point, and you can redraw that diagram. You will find it very easy to find equivalent capacitance of the given network. Question number 13. Find the equivalent capacitance between points P and Q for network of capacitors extended up to infinity. This type of network of infinite units, we have a capacitor CC connected to C here. In this one, what we first of all assume that let the equivalent capacitance be C dash. Let C dash be equivalent capacitance of the given network. We will just try to find out 1 unit of this network there, and we'll try to isolate that one. Suppose I take isolation from this point. What you have to see that whatever is our given network, and after isolation whatever we are taking, are the two giving the same circuit or not? So then let's just see. We had here C connected across, then we have 2C connected there in series. C is across, 2C series and across. But in this isolated part, we have first, between these 2 points, we have 2C capacitor in series. And then we have C in across the circuit there. Whereas earlier it was your C in across circuit and then we had 2C. So obviously this is not our proper choice of isolation of the circuit. So let's shift now this one, leaving this part. Let the isolation be done from this point. That means this 2C is here, and after that we are taking this isolation. So now you see that here you have C across, then 2C series. Here also we have C across 2C series, and it is the same in continuation. And it means this particular part of isolated circuit there, leaving one unit, is same as whatever circuit is given. So this is same infinite unit network. Of course, you can say that one unit is less, but since it is of infinite unit, so obviously the equivalent capacitance of this network will also be same. So let this part be represented by the infinite unit network, and its capacitance we have taken as C dash. C is this particular capacitor, 2C is this one, and for this entire part we have taken the equivalent capacitance as C dash, so it is C dash here. So you can see that now you have only three capacitors left. 2C and C dash, they are in series, so their equivalent will be 2C into C dash divided by 2C plus C dash. And now these two are in parallel, so equivalent capacitance will be C plus 2C into C dash divided by 2C plus C dash. And now this is a single capacitor of the given network between points P and Q, which we have already assumed that equivalent capacitance between P and Q is C dash. So this is equal to C dash. We'll just try to solve this for the value of C dash. So this C dash is basically C plus 2C into C dash divided by 2C plus C dash. If you simplify, this is your 2C square C dash 2C C dash divided by 2C plus C dash. So if you solve this, you will get the factors like C dash into C minus 2C plus C dash minus 2C equals to 0. Or you have the factors C dash minus 2C into C dash plus C. Now if I take C dash plus C equals to 0, that will give the value C dash as 0. But you know that the capacitance cannot be negative, so this is not possible. Whereas this term, we are left with this particular one, C dash minus 2C equals to 0, so that will give C dash equals to 2C. So this is the value of C dash, that is the equivalent capacitance of this network, and that is equal to 2C. Question number 14. For the following arrangement of parallel plates with plate area capital A and having plate separation between consecutive plates D, find the equivalent capacitance between P and Q. This is the arrangement. We have 4 plates. We have numbered them as 1, 2, 3, 4, and it is connected. 2 is connected to P and 3 is connected to Q. 1 and 4 are connected with the help of a conducting wire, and we have to find capacitance between point P and Q. We have the plate area capital A, plate separation as D. So here let's redraw this arrangement. P we have taken here, Q here. So P is connected to point plate 2, so we have written P2, and Q is connected to third plate, so we have written as Q3. 1 and 4 are connected with the help of a conducting wire, so both are at the same potential. So we have represented them as a single point here, 1 and 4. Now you see, between the plates 1 and 2, there is one capacitor, and capacitance of each one will be your epsilon naught A by D. So for 1 and P, since P is here, 1 is here, so we have represented one capacitor of capacitance C here. That means we have represented this particular capacitor. Similarly, for Q and 4, Q is here, 4 is here. So we have represented capacitor here. So this capacitor also we have represented at this point. and between P and Q, which is basically point 2 and 3. So it is, again, we have one capacitor here, so it is C. So that means this capacitor also we have represented. Now, if you look at this particular circuit arrangement, you will find that these two capacitors are in series. So their equivalent capacitance will be C by 2. This is another one, C, which is connected in parallel with this one. So these two are in parallel, equivalent will be 3C by 2. And since C is your epsilon naught A by D, so equivalent capacitance will become 3 by 2 epsilon naught A by D. So this is the equivalent capacitance of this particular arrangement. For second part, again we have 4 plates. We have numbered them as 1, 2, 3, 4. 1 and 3 are connected to point P, and 2 and 4 are connected to point Q. So let's once again show the plates having same potential at one point. So you can see here that 1 and 3, they are connected by a conducting wire to the point P. So 1 and 3 are at the same potential. So we have represented them here connected to the point P. Similarly, 2 and 4 are also connected to the same point, or with the help of same conducting wire, to the point Q. So 2 and 4 are here. Now, plate 1 and 2, that one will form one capacitor. So 1 is here and 2 is here. So we have shown one capacitor. This is for plates 1 and 2. Similarly, between 2 and 3, you have one more capacitor. So 3 is here, 2 is here. So we have shown the another capacitor. Between 3 and 4, again we have one capacitor. So 3 is here, 4 is here. We have shown the third capacitor. Now you can see all the 3 capacitors now, they are connected in parallel. So equivalent capacitance of this one will be 3 times C, as all plates are at equal separation, they have the same plate area. So their capacitance is epsilon naught A by D for each one. So equivalent is 3 times of this. So it is 3 times epsilon naught A by D. This is the value of equivalent capacitance between the points P and Q. Let's now take question number 15. A capacitor is made of a flat plate of area A, and the second plate having a stair-like structure as shown in the figure below. Of each stair is A by 3 and height D. Find the capacitance of the arrangement. So this is the arrangement shown here. We have a plate A, and this is the stair type structure. They have the area as A by 3, A by 3, A by 3, and width of the steps is D, so it is D here. Now you can see that it can be taken as if you connect this one as with one plate and this with one potential. So obviously we can consider that it is made of 3 capacitors. So suppose if I take this one as first one, this is say your C1. So this will be given as your epsilon naught A by 3 divided by D. This is the first capacitor. This is the second one. So this C2, if I call this as C2, this will be epsilon naught A by 3 divided by, now the separation is your 2B. So this 2B. And the third one, which is C3, it is this one. So this will be epsilon naught A by 3 divided by 3D. Now, if I take this as the point P and Q connected to a source or a battery there, it means these 3 capacitors, they will be connected in parallel. Because this is at one potential, all these will be at same potential. It means this capacitor is connected to point P and this is Q. This is also connected to P and Q. This one is also connected to P and Q. So all the three capacitors are in parallel. So for equivalent capacitance, C equivalent, in parallel combination, it is C1 plus C2 plus C3, which is epsilon naught A by 3 divided by D, epsilon naught A by 3 divided by 2D, epsilon naught A by 3 divided by 3D. So if you take epsilon naught A by 3 divided by D common, it is 1 plus 1 by 2 plus 1 by 3. And this is epsilon naught A by 3D. LCM is 6. This is 6 plus 3 plus 2. And this is your 11 epsilon naught A by 18. This is the value of equivalent capacitance of this stair type structure there, and equivalent we can write epsilon naught A by 18D. So this is all in this small discussion of different questions, conceptual type questions and numericals which we have done on capacitors.